Hey everyone, Mr. Fransky here. Today we're going to talk about 9.1b. That's about power series. Yesterday we talked about geometric series and the nth term test, and we talked about how geometric series with numbers are pretty simple, but maybe if we add some variables, we might be able to approximate some interesting functions using infinite series of polynomials, which is kind of cool. So let's jump in. Let's talk through the bell work here. I'm using a computer today that does not have a touch screen, so I have everything typed out. All the math is typed out. And I'm going to try to do a minimal amount of drawing because all I have is my mouse, and I think that would kind of be a mess if I tried to draw with it. So, bell work here, we've got some geometric series asking about convergence and also an nth term test problem. So if you want to give these a shot, you can, or if you want to try them with me, that's fine too. You might have to pause the video more often today because everything's written out, so I won't have to be writing along with you. So if you have to pause to write things down, that's just fine. So first question, we have 2 minus 2/5 plus 2 25ths minus 2 1/25ths, and first thing we want is just an expression for the nth term of the series. So like the third term, I want to plug in 3 into some equation or some formula, and that'll give me 2 25ths. So it looks like this is geometric. Our first term is 2, our next term is negative 2/5, so we multiply by a negative 1/5 to get there, then negative 1/5 again, negative 1/5 again. So it's geometric. Our first term is 2, and our r is negative 1/5. So that means the nth term should always be a times r to the power n minus 1. An is always a times r to the n minus 1 for geometric series. So in this case, that's 2 times a negative 1/5 to the power n minus 1. So if I want to get like the fourth term, I plug in 4 for n right here. That would be 4 minus 1 is 3. Negative 1/5 cubed is negative 1 over 125 times 2 is indeed negative 2 over 125. That would work for any value that you want, right? My joke with my advanced algebra kids back when I taught it was any value because it's n, right? Any value. Very funny, right? All right, moving on. So next up, they ask if it converges. So convergence of geometric series relies only on the r value. So in this case, our r value is negative 1/5. So an absolute value, that is 1/5, which is indeed less than 1. That's the requirement for a geometric series to converge. And so yes, it converges to a over 1 minus r. That's our formula for the sum of an infinite geometric series. So we put 2 on the top, that's our a. Then we have 1 minus a negative 1/5, which is 1 plus 1/5. 1 is 5/5, plus 1 more is 6/5. 2 over 6/5 is 5 times 2 over 6, which is 10/6. You can reduce that to 5/3, I suppose, if you wanted to. Be fancy. All right, next up, they ask if the series 1/2 plus 2/3 or 3/4, and the nth term would be n over n plus 1. They're asking if it converges. We actually saw this in class yesterday. And if yes, find the sum, and if not, why not? Well, as n gets very large, as we get towards the end of this series here, n over n plus 1, this is going to turn into 1. So the end of this, there really is no n, we're going off to infinity, but you're going to be adding 1 plus 1 plus 1 plus 1. It won't be exactly 1, but it'll be very, very close. So we're adding 1 and 1 and 1 over and over again. Then we're not going to be converging to anything. So we notice this is not geometric, right? 1/2 to 2/3, you would have to multiply by what? 4/3? 4/3 would get you here, I think? Yep. 4/3 will not get you here, though. So it's not geometric. The only other tool we have here is nth term test. And we notice that the limit of the nth term here is 1, right? Which is not 0. So that tells us right away the series diverges because that limit is not 0. Remember, if it's 0, that's not conclusive. We can't say that it converges if it's 0. But if it's not 0, automatically not going to work. So this is too easy. I think we should add some variables. Just imagine Newton and Leibniz having a conversation via phone or whatever they used back in the day, maybe tin cans and string, and saying, hey, you know what? Those geometric series, they're way too easy. We should add some variables to them. So yesterday, this was kind of the summary of what we talked about geometric series, right? If you have a geometric series, so a times r to the n minus 1 from 1 to infinity. So that'd be a plus ar squared, ar cubed. That is equal to a over 1 minus r as long as your r value is between negative 1 and 1, or in other words, the absolute value of r is less than 1. Those are the interval and radius of convergence. Remember, that's called the radius of convergence. This is the one picture I'm going to try to draw today, called the radius of convergence, because when you think about this on a number line, right here we've got 0. This is very challenging with a mouse, bear with me. There we've got 0. Over here we've got 1. Over here we've got negative 1. Oh my gosh, this is so hard. And if we drew a circle around 0, oh my gosh, that's the best circle I have ever drawn. Look at that thing. You try drawing with the mouse sometimes. All right, so if we think about this as being a radius of a circle, there's a little r right there. We go 1 to the right, 1 to the left. So the radius around the center of convergence, which is 0, is 1 to the right and 1 to the left. So that was what we learned yesterday. So our question is, instead of using an r here, why not use an x? So could this possibly be true? Is it possible that if you add 1 plus x squared plus x cubed plus x to the fourth, et cetera, off to infinity, that is geometric, right? It looks like it. It looks like we have a first term of 1, and we have an r that is equal to x, right? So instead of doing a over 1 minus r, this would be a 1 over 1 minus x. But 1 over 1 minus x, that's a function that, like, we've seen and we could graph, right? Like, that's odd. And so our sigma here, you're going to notice today I'm going to do sigmas starting at 1 and at 0 because I think it's useful. It's good practice to be able to see all of these. So I started at 1 because that's how we saw all of our geometric series yesterday. Convention for series really is to start at 0. But if you want to start at 1, that's just fine. As long as you're generating the correct terms, I don't care, right? The reason I started at 1 here is because the first term is 1, and we have x, which is our r value, raised to the power n minus 1 here. So we would get 1, x squared, x cubed. You could also start at 0 and just do x to the n, right? Because x to the 0 is 1, x to the 1 is x squared, x cubed, et cetera, et cetera. But the question is, are these things the same thing? Well, what we're going to do is we're going to take a look at a graph of it. So let's see what we can get out of here. Keep those. And I should have this ready to go over here. Yeah. So right here, what I have graphed is 1 over 1 minus x, right? And that's this red function right here. This is our 1 over 1 minus x. So the question is, as we keep adding terms, is this actually going to mimic the exact same function? So in the first graph here, 1 plus x. And that is, it's tangent right here, right? But it doesn't really do a good job of replicating the function. So let's add another term. If we add the next term, the x squared, now we notice it starts to kind of fit that curve a little bit. We have a parabola, which makes sense, right? The degree is 2. Now let's keep going. If we go to a cubic, we notice we have a cubic function, and notice we really start to do a nice job, kind of right around that center of convergence there, around 0, of mimicking the function. Now if you zoom in, 0 is the only place it's going to be perfect. Everywhere else it won't be perfect, but it'll be close. Let's add another term. So if we add to the fourth term, notice how much better we're getting already. And what you can do with Desmos, this is pretty cool, you can write it in sigma notation, and I have it going to k. So right now, I've got it at k equals 1, right, which is just a horizontal line. If I go to k equals 2, oh, come on, buddy. If I go to k equals 2, I get that, that exact function we had up here. 3 should give me that parabola, right, because I'm to the n minus 1 here, which is why the degree is 1 less, right? And then 4 should give me that cubic. 5 is the last one that we looked at, right? That was the quartic polynomial right here. Now, as I keep going, notice what happens. That function does a really nice job, right? And this is just a polynomial, right? It's just a polynomial, and I'm adding an infinite number of terms together. If I keep going off, like if this were to get bigger and bigger, I've got it stopping at 20. But notice it does a really nice job. Where does it do a nice job? Between -1 and 1, which is exactly what we tell ourselves in this problem, right? We go between -1 and 1, as long as absolute x is is less than 1, so between -1 and 1. This function, this polynomial with an infinite number of terms, is going to do a perfect job mimicking this thing. Now, it's only good between -1 and 1, right? Over here, terrible, right? This function goes down really fast. The gap, the error over here would be huge, right? But the more terms I have, the better this blue function, I guess it's kind of purplish, well, blue and purple because it's mixing with the red, but this blue function is going to do a much better job the more and more terms I have of mimicking this function. The closer you are to the center, the better it will be, right? Further over here, notice there's a little gap here, but if you have an infinite number of terms, it'll be perfect between -1 and 1. Wow, that's pretty crazy. So, what that means is that we can actually do this with any function that has this shape kind of that looks like an a over 1 minus r. So I have 3 here that we're going to kind of focus on. So what we're going to do here is we're given the function. We're going to try to write out a series of, like a sum of a bunch of x's, 1's, numbers, whatever, x squared, x cubed, to try to mimic this function, right? We're going to do that for each of these 3. So we're going to write the first 2 terms of the series, and we're going to try to give sigma notation as well. And we're going to give the radius and interval of convergence for x. And the whole idea there is that the radius, whatever r is, whatever we're multiplying by every time, that's got to be less than 1 in absolute value, right? Because that's the only way that a geometric series is going to converge. So we're kind of going backwards here, right? We're starting with the a over 1 minus r, and we're going to try to go backwards to be able to get out what the geometric series is. So for this first one, it looks like our a term is 1. Right, so we're always going to think if we see a fraction like this and we're asked for a polynomial or an infinite series, we're always thinking, well, it looks like a over 1 minus r. And so it looks like our a value is 1, And if 1 minus r has to be 1 plus x, you can do the algebra. I mean, it's pretty easy to see. Well, we have the 1. That means that our r has to be a negative x. But you can do the algebra too. We're going to see some in a second that are going to have some harder algebra. So if you add the r, though, and you subtract the x and subtract the 1 from both sides, you're going to see that r is equal to negative x. So what we should have here is we start with our first term of 1, and then because it's geometric, we just multiply by that r every time, right? So this is a over 1 minus r, so our r is negative x. We have 1, then we have a negative x, then a positive x squared, then a negative x cubed. This is an alternating series, right? Because our r is negative. So what we have here, if you think about the sigma notation, this is kind of the geometric standard that we've used before, right? We have our first term times the r to the n minus 1. But if you wanted to start at 0, you could just do negative x to the n, right? That would give us 1, then it would give us negative x, then positive x squared, then negative x cubed. That would work out just fine. And that should be good. That should be good whenever r is between negative 1 and 1, or the absolute value of r is less than 1. So that means absolute value of x has to be less than 1. Well, absolute value of negative x and positive x are the same thing. So that means absolute x has to be less than 1. In other words, negative 1 is less than x, less than positive 1. Again, this is the radius of convergence when we have that absolute value there. This is the interval of convergence when we have the actual interval that the numbers, the x's between negative 1 and 1 will work out. So let's take a look at the graph. So if we graph 1 over x plus 1, that's just 1 over x shifted to the left by 1. Let's take a look at our Desmos here. Have this one ready to go. So we've got our 1 over 1 plus x. So it's 1 over x just shifted left 1. And now I have this guy again, so we're doing this, looks like it started at 1 again, so we have negative x to the power x minus 1, or n minus 1, because we have a 1 in the front there. And as we start to increase how far we're going, so this is just 2 terms, and 3 terms, 4 terms, 5 terms. And as we see, I always kind of like to watch that little tail over here. It's like it's whipping around the red function. It's kind of cool. So as you go, it gets better and better and better. And once again, where is it better? It's better, it's best right between negative 1 and 1, right? Between negative 1 and 1, that's where it mimics the function. It does not do a good job after we get beyond 1 or to the left of negative 1, right? Which kind of, you can also see because we have that asymptote there, right? It's not going to jump down and do the other part of the function. So as we go, it gets better and better and better, okay? And if you want to mess around with this on Desmos yourself, you can increase this to like 1,000 if you want to and see how good you can get that gap down there, but it's kind of cool. So using geometric series, just to kind of mimic these functions that look like an a over 1 minus r using an x. That's really all we're doing right now. So let's take a look at the next one. So you may, if you want to try these on your own, feel free. I'm just going to kind of keep plowing forward. Let's see what we get. All right, that was the first one. And the next one. So now we have x over x, or 1 plus x. I think what's going to change here is our a. Notice our r isn't really going to change because the bottom is still 1 plus x. So we have a is equal to x. That's our top value. So the first term is x. And once again, r is going to be negative x. You can do the algebra on that, but just set 1 minus r equal to the bottom, solve for r, and you'll get negative x. So this time, our first term is x. Our second term will be negative x squared, then positive x cubed, then negative x to the fourth, positive x to the fifth. We're multiplying by negative x every time. So the sigma notation for that, first term is x, so we have that in the front. Then we have our r value, which is negative x to the n minus 1. If you want to start at 0, you can just do x times negative x to the n. Plug in 0, you get a 1 there, so you'd start with an x. Plug in 1, you get a negative x, and you have a negative x squared altogether. Either way works, though. You could start at n equals 5 if you wanted to, and make this an n minus what would be 6 at that point. You can start wherever you want. It doesn't matter, as long as you generate the correct terms of the series. So, where is this guy going to be good? It should be the same as last time. Our absolute value of negative x has to be less than 1. In other words, absolute value x is less than 1. So x has got to be between negative 1 and 1. Radius with the absolute value, interval with the left and right bounds. So if we graph x over 1 plus x, this one is not like a translation of 1 over x. It actually is, but the algebra is a lot harder, so I'm going to spare you that. So we take a look at the graph. Once again, we start off just having a nice tangent line right at 0. I just have this guy starting at 1, so we have our first term and then times our r to the power n minus 1 here. And as I increase this, notice, once again, it's a different function, but it's still doing a really nice job between negative 1 and 1. The more terms I have, the better it mimics, the better it relates to that function, right? Between negative 1 and 1, we do a nice job of following that function right in there. More terms you have, the better job it'll do. So again, what are we doing here? We're taking a function that looks like an a over 1 minus r, and we're saying, well, if we consider the top is our first term, and the bottom is our 1 minus r, and we figure out what r is, and as long as that r is between -1 and 1, then we're going to do a nice job of mimicking this graph by using a polynomial, which is a much simpler idea to use. Alright, got one more. This one's a little trickier as far as like finding r, but really it's not that bad, as long as you can do a little algebra. So, looks like our a, once again, is going to be 1. What about our r this time? Looks like 1 minus r is equal to 2 minus x. So I kind of showed a couple algebra steps here. The way I do it is I add x to both sides, and I add r to both sides. So we have 1 plus x is equal to 2 plus r. And then if you subtract 2 from both sides, you would have -1 plus x equals r. Another prettier way of writing that is just r is equal to x minus 1. So we have a more complicated ratio this time that we're going to multiply by every time. But works the same way. First term is 1. Next term, we multiply by x minus 1. Multiply by x minus 1 again. X minus 1 again. You're going to keep doing that. So our geometric kind of standard way of writing it, we start at 1. We have our first term. Then we have x minus 1 to the n minus 1. If you wanted to start at 0, you would just have x minus 1 to the n. We don't need the 1 in the front. Right? I wrote it here kind of for the sake of seeing what's going on. But we got x minus 1 to the nth power. To the 0 would just give us 1, then the first, the second, the third, the fourth, etc., etc. So, where is it good? Well, this one is a little bit more interesting. The absolute value of our r has to be less than 1. That's always how geometric series work. That means that x minus 1's got to be between -1 and 1. And then if we add 1 to both sides, which I did incorrectly, it should be between 0 and 2. That should be between 0 and 2. I'm actually going to change that right now. So it should be between 0 and 2. All right, back to me. Okay, so if we're between 0 and 2, because if I had added 1 correctly instead of subtracting 1, then we should be good. So if we graph this thing, this guy, if we clean the x a little bit, if we pull out a -1, we have -x minus 2. So what this should be the 1 over x function. This negative is going to flip it over the x or y axis, either one way you want to think about it, and then shifted right to. That should be what we're looking at. Let's see what we got. So here we have 1 over 2 minus x. So we're shifted to the right by 2, right? That's the, if you flip this around, right, this will be the same as 1 over x, negative quantity x minus 2. So shifted right 2, and we are flipped, right? Instead of being kind of up here and down here, we've been flipped over, and so we're in like quadrants 2 and 4 instead of 1 and 3. So again, if we increase here, we should be in the interval that I ended up with, not the one I started with. So it looks like we end up with a really nice interval between 0 and 2. So what we're going to talk about in a second here is what's called the center of the series. Where is this thing centered? Looks like it's centered at 1, right? And we see this kind of in here, this x minus 1. That makes it look like it's been shifted right 1. So our center is at 1, and we do a really nice job with a radius of 1 to the left and right? So we're centered at 1, and then we're good to the left 1 and to the right 1. Cool. All right. Moving right along. So, we're going to get a general definition of what a power series is here. Because power series, all of these that we've been looking at have been power series, right? This guy, x minus x squared plus x cubed, this is a power series because x is increasing in power. The next one, this guy, also a power series. We have this x minus 1, but we're also increasing in power as we go. So instead of calling it like an infinite polynomial, we call this guy a power series. Power series is anything that has x's that's got powers going on, basically. So they can be centered at different spots. If it's centered at 0, it looks like this. Okay, so notice now, from now on pretty much, unless we're dealing with geometrics, we're going to pretty much start at 0. If you want to start at 1, that's fine. You would have n minus 1 and both the subscript and the superscript here. But what we've got here is we've got something with coefficients. This Cn is just some sequence that's in front of x's that are increasing in power. So I don't really care what it is. It could be that this is geometric. In fact, in the geometric series we were looking at, these were all the same, right? Because C0 would be like my first term, and then it would still be my first term times x, then still my first term times x squared, and x would be my r, right? But C could be whatever you want. It could be an alternating series. It could be something like e to the n. I mean, it could be whatever you want. These C's could be any numbers, right? All we're really saying here is that we have some kind of coefficients that are in front of x's that are increasing in power. That's what's going on here. If we center it somewhere else, like the last problem we had was centered at 1, Really all we're doing here is we're shifting horizontally, right? So we're shifting horizontally to the right by a units. So the difference here, and we're going to see this a lot more when we get into 9.2 with Taylor polynomials, but this centered at 0 up here, this would be very good close to 0, right? For x values close to 0, this will do a nice job of kind of approximating a function. So like the first couple of problems we looked at did a really nice job close to 0, right? And then like between -1 and 1. Close to 0, though, is where it was best. Like especially if we back this up a little bit. There we go. So it does a nice job close to 0. The further we get away from 0, not so good, right? The last one we looked at, this one was centered at 1. Notice it's really good close to 1, not so good further away, right? The further out that we get, the worse it's going to be. So close to the center, we tend to have really good approximation of these functions, right? And it kind of depends on what those c values are. We're going to see lots of different situations where we have lots of different things. We've only really looked at the geometrics so far, but those can be whatever you want. And so the question of when could it converge really depends on what that sequence is. There are some where it's a sequence that is really like doesn't grow very fast at all. So it could converge in lots of spots. It might grow very fast, and it might not converge very far away from the center at all. So here's what could happen. It could converge at an interval around the center. So that would be a conditional convergence, kind of like a geometric series, right? For a geometric series, we know that R value, the absolute value of R has to be less than 1 in order for it to converge. So like in that last example we had, we needed that absolute value of x minus 1 to be less than 1. So very close to its center of 1, between 0 and 2, it was good, right? So that's one case. It could converge around the center for some specific values close to the center. It also could converge at every x value. We're going to see some series like this that will converge everywhere, every single x value, no matter, like it doesn't depend on these c values at all. It could work that every single x will actually make it converge. It also could work where no x makes it converge except the center. So what that means is up here, like if you plug 0 in for all these x's, I don't care how many terms you have. You could have an infinite number of terms. If you plug 0 in for every single x, what's the only thing that's going to be left? C0 is the only thing that's going to be left. So you have an infinite number of x's. They all go away if you plug in 0, right? So at the center it will always work. Down here, same thing, but at a. If you plug a in for every single one of these x's, if you plug a in for this x, and this x, and this x, they're all going to disappear. Everything except for the C0. So at the center, it will always converge, no matter what sequence you have for those c's. And it might be possible that if you move just a little bit, like here, maybe like 0.1 and -0.1, like those will work. At some point, it might not work anymore. That's this first case of a geometric. Or it could be that if x is 1,000, this will still converge. Maybe those c's become small so fast that it doesn't matter what those x's are, and it'll always converge, right? These are kind of the three situations that could happen. Okay? So, here's an example of a power series. Our c is just -1 to the n. So it'd be 1, -1, 1, -1, 1, -1. And we're centered here. We're centered at 1, right? We have our x minus a here is centered at 1. So the question here is, what's the function? Where's it centered? What's its radius convergence? Well, let's write out the first few terms first. So if you plug in 0, -1 to the 0 is 1, x minus 1 to the 0 also 1. So we get 1. Next term is going to be negative. This is going to alternate every time. Because if n goes up, if n is even, it'll be positive. If it's odd, it'll be negative. So we have a negative term now, and we have x minus 1. We have plus x minus 1 squared, then minus x minus 1 cubed. That's going to keep going, right? We're going to keep adding these terms. The power will keep going up. It'll keep alternating. That's all it is. So what do we notice about this? Well, it looks like it's geometric, right? It looks like our first term is 1, and it looks like our ratio is negative x minus 1 every time. So here, it's geometric. The first term is 1, and the ratio, we're just multiplying by negative x minus 1 every time, right? Which is 1 minus x if you distribute that negative. Okay? So if we want to know what the function is, we can just do a over 1 minus r, right? As long as we have our r less than 1, right? Absolute value of r has to be less than 1. So we'll get to that in a second. But first of all, the function should just be 1 over, so a, which is 1, right? Our first term is 1, over 1 minus r. That's 1 minus our r here, which is 1 minus x. Distribute the negative, that's 1 minus 1 plus x. The 1's cancel, that's 1 over x. So this polynomial here, as long as we go far enough, should do a nice job of approximating 1 over x. Now, when is it good? Looks like I actually didn't write that down. This would be good when the absolute value of r, this guy right here, let's write this out, why not? So what we need is the absolute value of r, which is negative x minus 1. Oh, it's painful. X minus 1. Whoop, close it. Would have to be less than 1. And I'm going to spare you the gory details because I don't want to write all the algebra. But the negative doesn't matter, right? Because it's absolute value, so who cares? So I'll just make it positive. And then if you made it between negative 1 and 1, and then you added 1, once again, this would be good between 0 and 2. So 0 is less than x is less than 2. This is going to be good. This is what I get for not writing out the interval, okay? So let's graph it and see what we get. Okay. Go to Desmos. Here we have our 1 over x. And here I have, this time I'm going to let the v go up to 100. So we're actually getting a really nice picture of what's going on here. Notice it's centered at 1, so it's perfect right there, even when v is very small. And then as we go, I like kind of how it does the hula dance as we go, right? So the more terms you have, the better and better and better it does of approximating between 0 and 2. Notice even by the time I get to 100, we still see a little gap here, right? Because we need an infinite number of terms for it to be perfect between 0 and 2. At 0 already, I can't even tell the difference, right? Because it's going up to that asymptote. It's rising so fast that I can't tell the difference between them. But over here, as we flatten off, there's a very stark change, right? It's not an asymptote because this is a polynomial. Right now, a degree 100 polynomial, right? So that's why it goes up on both sides, because it's even. If you pick a number that's odd, so that's 97, right? This time it goes down, right? Because we have an odd degree polynomial. Cool. But good between 0 and 2. All right, so this is still too easy. So Leibniz got up on the phone and he's like, Newton, dude, still too easy. We got all these x's, but let's do some calculus on this. So we know right now, right, that we have this geometric relationship between 1 over 1 minus x is the first term, 1, and then we have this common ratio r of an x value here. So we'd have 1, and then plus x squared, then plus x cubed, right? That's the sum from n equals 0 to infinity, just x to the n, as long as the absolute value of x is less than 1. So the question here is, any idea how we could get a series for 1 over the quantity 1 minus x squared? Well, this guy is not geometric, right? We have this square on the bottom. If you were to expand this out, you would have, what, 1 minus 2x plus x squared, I think? And that would not be geometric. We could maybe try to figure out what r would be in that case. But I think there's an easier way to do it. How is this related to 1 over 1 minus x as far as calculus goes? Well, generally when you're adding these degrees on the bottom, that looks like some kind of a derivative. Let's check it out. I think it is the derivative. Let's see. So if we derive the original function, 1 minus x to the negative 1, the negative 1 comes to the front. We have 1 minus x to the negative 2, and then we have to chain, right? Don't forget the chain rule. So we have to multiply by a negative 1. The negative 1 in the front and back cancel. So we just have 1 minus x to the negative 2, which is 1 over the quantity 1 minus x squared. Very cool. So could it possibly be that 1 over 1 minus x squared, that's the derivative of the left side. So it should make sense that if we derive the right side, this should be the same. So if we derive the right side, the first term is 0, then we get a 1, then we get a 2x, then a 3x squared. Notice this is not geometric, right? Multiplying from here to here, you have to multiply by 2x, but 2x does not get me from here to here. Right? That wouldn't work. Okay? So this is not a geometric series. So we are getting to a place now where maybe we can find some power series for things that are not necessarily geometric. Well, that's a pretty cool idea, right? And if you look here, you can really just do the calculus on the thing inside of the sigma. Move the n to the front and drop the power to the n minus 1. That's all you have to do. But it's still only going to be good between negative 1 and 1. So let's take a look at the graph here. I didn't go to check the graph, but let's check the graph. So here, I have 1 over the quantity 1 minus x quantity squared. And so what we're going to do is we're going to sum from 0 to k, nx to the n minus 1, right? And so start increasing this k. So notice we have a volcano kind of looking function here. This is the derivative of 1 over 1 minus x. And as we go, once again, we have a really nice function. And where is it good? Good between negative 1 and positive 1 in that same radius of convergence. So when you start doing calculus on these, whatever the original radius was, that is also going to be the new radius. You cannot expand it. It doesn't get bigger, it doesn't get smaller. It's good in the exact same place. Right? So, yeah. So we have this idea that it's not geometric. but doing the derivative of the left side, the derivative of the right side, both give you the same thing. So this kind of new way of using a polynomial to approximate graphs, it works when you do the calculus on both sides, which is kind of cool. And this should have come up one piece at a time, but I guess we're just going to have to talk about it. So how about a power series for negative natural log of 1 minus x? Well, natural log is the antiderivative of 1 over 1 minus x, right? The negative comes from like unchaining, if you want to think about it that way, right? So it should work out that the antiderivative of the right side should give me this natural log, which is weird. This is the first time we've seen something that's not a fraction, right? But the calculus works out, right? Antiderivative of 1 over 1 minus x is negative natural log 1 minus x, so it should work out fine that the antiderivative of the right side should give me the left. So it looks like we would have an x, then we have an x squared over 2, then x cubed over 3, right? Antideriving polynomials, easy, right? Antideriving stuff like this, gross, okay? But once again, we can just take our sigma notation and just antiderive the inside of it, right? X to the n plus 1 over n plus 1. That's it. And it's going to be good in the exact same place as it was before. Let's take a look at that graph. This is the last graph we're going to look at today, I promise. So, as we increase our k here, so notice we have the negative natural log of 1 minus x graphed here, right? Negative is going to flip it over the x-axis. That's why it's kind of looking upside down. And the 1 minus x is flipped it over the y-axis as well, and it shifted it to the, gotta think about this, the right one. Yes. So, as we graph our sigma here, and we start to increase our degree, notice once again, really great job of approximating our function between negative 1 and 1. Okay. So, centered at 0, and some of you might be saying, is the radius always 1? Well, no. If this was like a 2x, or something, then our radius would shrink to a 1/2, right? So you'll see some in your homework where the radius is going to be different, but it's still really not that hard. You just do the math and make sure that your absolute value of r is always less than 1. Okay? So, possibilities are endless, and if we want to stretch our brains a bit, could we think of a power series for tangent inverse? So, really, anything that can be related through a derivative or an antiderivative to a function that has the form a over 1 minus r can be created using a geometric series and then using calculus on the series. So what do we know about tangent inverse that looks something like a fraction like this, like an a over 1 minus r? What's the derivative of tangent inverse? That's 1 over 1 plus x squared, right? 1 over 1 plus x squared, well, that's geometric, with a equals 1 and r is negative x squared. So we can write that out. Right? It's first term 1, then negative x squared, positive x to the 4th, negative x to the 6th. We're just multiplying by negative x squared every time. So I wrote that. You could write this as like kind of a typical geometric way, but what we're going to see a lot in the future is alternating series just always throw a negative 1 to the end in the front, because that makes it alternate. And then I just have all the even powers of x. That's just x to the 2n. That's going to work when absolute value of x squared is less than 1, because we need our r to be less than 1. In other words, like when you square a number less than 1, it's just still going to be less than 1. So absolute x has to be less than 1. They're just like every other one we've seen today. So now if we antiderive both sides, antiderive the left, we get tangent inverse of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and that's going to keep going. So notice this time it's all the odd powers because we added 1 to all the evens. So we're still alternating, and all I did was add 1 and divide by the same thing. It's kind of a gross exponent, but it's just all the evens. You add 1, that makes them all odd. Now on the bottom you divide by the same thing. And that'll still work when absolute x is less than 1. I don't have a graph of this. Yeah, good, because I didn't call for it. I don't have a graph of this, but if you want to try graphing that on your own, it's probably good practice to kind of try it in Desmos and see what you get. All right. Last thing I want to say today. So this is where we're going in 9.2. In 9.2, we start to look at a very special set of functions called Taylor polynomials. These are infinite polynomials, which are simple functions, right? Polynomials, we know how to derive them, we know how to antiderive them, it's pretty easy, that mimic more complex functions. So what I want you to do is take this guy right here. And if you forgot what factorial is, factorial just means you multiply by all the numbers less than it. So like 4 factorial, 4 times 3 times 2 times 1 is 24. So n factorial in general, you just multiply by all the numbers less all the way down to 1. You don't include 0, because if you included 0, then every factorial would be 0, right? Don't do that. So this function, we have 1 plus x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial. In general, x to the n over n factorial. So what Taylor polynomials do is they try to mimic more complex functions. So this is a very popular, well-known function. And what I want you to try to do, and I'm not going to give you the answer, I want you to give it a shot, and then we can talk about it in class tomorrow, But I want you to try to take the antiderivative and the derivative of this function. So if you derive this function, right, you have 0, and then you have a 1, then you have 2x over 2 factorial, 3x squared over 3 factorial. Cancel some stuff out, see what happens. Do the same thing with the antiderivative. When you antiderive, you have to be a little sneaky with the plus c, but I think you'll kind of see where this is going. And if you do those two things, if you derive and antiderive, and you see what happens to the function, I think you might be able to guess what this function is. So give it a shot. Try it out. If you get super excited about it, like I always do, send me a text on Remind, and we can talk about it in class tomorrow. All right, so another long video, but hopefully it was less painful than yesterday watching me try to struggle through writing on a screen that wasn't showing up. If you have any questions, throw me a text. Otherwise, I love you guys. That's why I'm here. Have an excellent day.